All right, welcome to our technical topic webinar for February. We have some incredible presenters today. The topic today is BIPV, Advanced Glazing and Energy Solutions. And we're going to be hearing from Clearview Technologies. And we've got some incredible people online today who I'll be handing over to very shortly. We've got Jamie, we've got Tal, we've got Mikhail, and I believe we've got someone else, Doug. So welcome all, and thank you so much for joining us today. Just before I hand over, just a few common questions that pop up usually throughout the presentation. We will send a copy of the slides and the video recording to all attendees and registered attendees today. And there will be a certificate of attendance that will be sent through afterwards. The link to that will be sent at the end of the presentation. Just a quick overview on who EIT is. So I am from an engineering institute and we run these technical topic webinars each month, and we try and look at topics in all fields of engineering and the technical space. So we are specialists in engineering and we offer qualifications all the way through to a doctorate of engineering. And I will now hand over to our wonderful presenters today.
So Carolyn, would you like me to share the screen now? Is it?
If you want to just introduce yourselves on this slide, yep, and then we can hand over to you to share your screen. Thanks.
Sure. Okay. So my name is Jamie. I'm the Chief Operating Officer and General Counsel for Clearview Technologies Limited. We're an ASX listed company in Australia. We operate in the building integrated photovoltaics or window integrated photovoltaic space. And I'll explain that as we go along, and I'll have the other gentlemen who are joining me today speak to some of the more scientific and technical aspects. So joining me today is Dr. Mikhail Vasilyev. He's our lead scientist and was integral in developing the technology from the outset, which was originally developed with Edith Cowan University in Western Australia. Mr. Zhang joins me as well. He's a senior engineer, also worked with ECU and also was integral in an early stage in developing the technology. In addition to those two, we've also got Doug Hunt, who is a business development manager who recently joined us, but it also comes with a strong technical background, more on the solar side and sort of complex electrical installation projects. Also on the call, but in observing, Victor Rosenberg, the CEO and founder of the company. He was also integral for the development of the technology in an early stage. And we're also, understand, I've just seen Dieter Moore, who's our European CEO, has joined the call as well. So he's based in Austria, managing our European market entry. Carolyn?
Yep, I'll hand over to you guys to share your screen and the presentation slides.
Sure.
Thanks.
Is that coming through?
Perfect. We can see very clearly.
All right. All right. So let me just get this going here. As I mentioned, we're in the BIPV and window integrated photovoltaic space. What I'd like to talk to you about today, it's more than just the sort of the building integrated photovoltaic side and window integrated photovoltaics. I'm also going to run you through the sort of drivers that are coming into play, moving towards the need for these sorts of products. So I'm looking at the climate imperative. I'm going to just take you through some of the drivers that are occurring in the building and construction space and the role and impact on greenhouse gases and the contribution to the climate crisis. I'll then look at some other BIP and BAPV solutions, and I'll come towards the end of the presentation. We'll talk about window integrated photovoltaics and some of the advanced glazing solutions that are available, including our own product. Just to kick it off though, I'd like to just run you through a couple of short videos that sort of show our product so you sort of know where we're coming from. So if I can just do that. Hopefully this will work.
Clearview PV have developed technology that allows clear glass to convert sunlight into electricity. Glass building facades have the potential to become massive solar panels. The ultraviolet and infrared components of sunlight are filtered using our specially developed integrated panels, allowing 70% of the visible light to pass through. Ultraviolet is converted to infrared and deflected to PV cells, which harvest the energy around the panel edges. Currently, we can generate 30 watts peak per square metre. Each window shown here can generate 500 watt hours per day. 200 windows would power 400 25-watt lamps for 10 hours. To find out more, visit clearviewpv.com.
That just sets the scene for the technology. We'll come back to explain that a lot more towards the end. I'm just going to run another short video, if I can, which shows the product.
For us, it's about another Australian first and really getting ourselves out there in terms of thinking about the next phase of our integrated energy and solar rollout. So there's lots of roof space, and we'll eventually take all that up, and we can take a functional form that sits around us here in Chadstone, for example, windows and glass, atriums, and turn that into clean energy for our centres.
Solar panels are not windows. You can never use a solar panel wherever you want a window. Our Clearview PV glass are windows. They can be used wherever windows are, anywhere in any building, in any structure.
So innovation is really important for the shopping centres, but also important for the industry. This is about really thinking about the next 2 years ahead and what might be possible, but it also really builds on the innovation platform that we've built, from robotics to smart bins to smart cities. And this is really the next iteration of that, and constantly challenging the team to come up with new things. Not every one of them works, but we always learn something every time, and we're better because of it.
So that was just a fairly small trial that we did at an early stage in our development. The point of the trial was for us to demonstrate the performance of the product, and for Vicinity Group, which is a big property owner in Australia. They have many shopping centres and the like. For them, it's an opportunity to explore new technologies. I'll come back to explain a bit more at the end on that trial and how it went. All right, so that brings me to the sort of start of the conversation today. Back in 1994, I was a law student, and as I chose as one of my electives the subject environmental law. We had to write a research paper at the time, and most of the other students were writing on things like mining rights, waterways, ozone protection and the like. I chose to write on what then was called global warming, and the laws and sort of protections that did or did not exist around that. In short, there were none or very few that had any binding force at the time. Anyway, for the purposes of writing my paper, the Intergovernmental Panel on Climate Change, or the IPCC, had already been formed with their work having started in around 1987, with their first initial report being released in 1990, and a more substantive first complete report in 1992. Since then, in October of 2018, the IPCC has released its Special Report 15. Yes, the numbers have added up over that time. And earlier this year, they released what they call their Sixth Assessment Report, or AR6, just ahead of the COP26 conference in Glasgow. When the Special Report 15 came out at the end of October 2018, the report, at least according to the chairman of the working group, Pao Mao Zai, said that in order for us to respond to the global warming situation, it's going to require far-reaching and unprecedented changes to human behaviours. They also said that we're already seeing the consequences of 1 degree of global warming through more extreme weather, rising sea levels and diminishing Arctic sea ice, among many other changes. The UN Secretary General, commenting on the report, also said that the report was an ear-splitting wake-up call to the world, and it confirms that climate change is running faster than we are, and we are running out of time. This year, when the AR6 report came out, the new UN Secretary General called the report a code red for humanity. Very serious stuff. One thing to take away, though, that I've taken away from the Special Report 15, though, is that a large focus in the report was on the role that buildings and cities play in how we respond to and look at climate change. They also looked at sort of solutions, and of course you would expect they talked about ramping up installation of wind and solar power, but they said that the coming period is critical. We need to act now. Importantly, and for us and the space that we're in, buildings and construction is a major contributor to climate change, and we're going to be expecting to see by 2060 another 230 billion square meters of buildings that are built. This is the equivalent of adding an entire New York City to the planet every 34 days for the next 40 years. In the context of all of this, the focus for architects, facade engineers, engineers that support this space is there needs to be a real effort and focus on construction decarbonisation, really as a paramount consideration at all stages of the design process for new buildings and even retrofit opportunities. On the basis of that, there is a sort of a groundswell and a direction now towards the designing of net zero buildings or zero energy buildings. And I'd like to talk to you briefly about some of the drivers that are helping that along. In 2019, the World Green Building Council released its report identifying that 39% of global energy-related carbon emissions are responsible for greenhouse gases. So they're contributing 39% to greenhouse gas emissions globally, with 28% coming from the in-use phase to heat, power, and cool them, 11% and 12%, depending on who you talk to, for the construction phase. So the phase before the building is completed and operational. The one thing the report says, which I think is good and means that we're actually operating in the right space ourselves, is that buildings actually represent one of the greatest and most achievable ways to respond to the climate emergency that's facing us. During 2019, the World Green Building Council also announced its very ambitious new project called Advancing Net Zero, which aims to make all buildings net zero by 2050. For their purposes, net zero relates to buildings that either are net zero energy, they produce as much renewable energy on site as they use annually, or they're net zero carbon. They produce net zero carbon emissions on an annual basis. More granular or detailed approaches also look further at the embodied carbon in the construction itself, the 11% or 12% that I mentioned earlier, and whether this can then be paid back over the life of the building, or preferably much quicker. So that's all well and good, but how do we really do this? And this is really just a question to everybody. We may have got this wrong, but the two simplest things that come to mind in thinking about how to move to zero are through the generation of clean energy, on site preferably, and insulation. Obviously implemented through clever building design and clever architecture. For us, window integrated photovoltaics combine these two things together, both solid, strong insulation, but also power generation on site. So in essence, we need to insulate better whilst harnessing a natural renewable energy to produce power. It sounds simple, but in practice it's difficult. The World Green Building Council also set up a net zero building carbon commitment, and in May of 2019 they had a large number of signatories. Since then, the number of signatories has increased to around 109 today. So you see the likes of big global building companies, but also big global architecture firms like Foster's in London. In Australia, we have people like Dexus and AMP Capital, Frasers, but also people like JLL, real estate type firms, and Lendlease and the various Lendlease companies. Other companies include tech suppliers such as Siemens AG. Cities are also signatories to this, and states, but not countries. In relation to Lendlease, for us, we recently recruited John Downs onto our board. John is the global head of facades for Lendlease and based in London. Lendlease has itself set an even greater target for its response to climate change. It wants net zero by 2025, 5 years ahead of most others, and absolute carbon zero by 2040. That's covering the embedded carbon aspects. Other sorts of things that have emerged in this space that are driving this direction are the Net Zero Momentum Tracker. This tracks the largest property companies in Australia on the ASX 200 with their move towards net zero. It's a place for them to compare notes, share their learnings. It's not really about the optics. It actually is genuinely about trying to respond to climate change. Other drivers from a top-down approach are regulatory and quasi-regulatory and sort of industry-based drivers. So you see the European Commission has the Energy Performance of Buildings Directive. That flows through to member state legislation in most European countries. Similar legislation throughout the world. So we also see places like New York has Local Law 97, similar law in Chicago, where the buildings that already exist need to be upgraded significantly, starting from 2024 on. It's a disincentive approach. So the idea is that if the buildings aren't refurbished, then fines apply. A lot of other approaches are more incentive-based, where there's an incentive. So in New York, you see both. There's solar tax credits, which are an incentive, and then they have potentially the fines that are coming from 2024 on for not responding to climate change in the building space. Industry-based and quasi-regulatory include things like BREEAM, BREEAM. This is a code that was developed originally in the UK, but it's now been adopted by more than 80 countries worldwide. LEED in the US and Canada, Green Star in Australia, a plethora of these things. But the one I'd like to just briefly mention is Zero Code. This started in California, but it's also been adopted in a couple of states in China. The Zero Code takes the traditional green building codes ideas, including you must have an efficient building envelope, you must have good daylighting, you must have passive heating, cooling, ventilation, introducing efficient systems into the building, so regenerative braking on the lifts, advanced building management systems and controls to control the climate. That's one aspect, but then the Zero Code takes it further and says, that's all well and good, but you really actually need to include on-site renewable energy on the building itself or very close to the building. If you can't do that, it needs to be reasonably close by. The energy shouldn't have to travel far to reach the building. It can be wind, solar, hydro, geo, really whatever, but ideally on the building itself. And if you can't achieve on the building or near the building, then you need to look at some renewable offsets. So all of these things may not be enough. Foster & Partners, one of the world's biggest architectural firms, did Bloomberg's headquarters in London, which opened in 2017, not 2,107 that it says there. A year later, in 2018, they won the most sustainable building in the world, and won the Reeva Stirling Prize, which is the Royal Institute of British Architects. The building uses 73% less water, 35% less energy. It got the highest possible BREEAM certification of outstanding. A few months after the building opened, the head of design at Foster & Partners presented at a conference in Beijing, and he described this new building as a 3-degree building. It's 1.5 degrees above the 1.5 degree Celsius cap that is the level that we're seeking to prevent the runaway climate change. Importantly, my observation on this and our observation here at Clearview was that this building, it didn't include energy generation in the actual facade. If you had thought about that and you had done that as well, you could have brought the 3 degrees down a bit lower, probably not to 1.5, but certainly lower than 3. The building is very clever. It introduces ventilation through those fins you can see in the picture there. It's got a lot of energy efficiency built into it, a lot of electronics controlling how the systems work inside the building, but they don't integrate energy generation in the facade. So that's what I'd like to talk to you about now. So building integrated photovoltaics, they're a part of the net zero solution. So briefly, I'd just like to introduce you to what the difference is between what building integrated photovoltaics is versus building applied photovoltaics. So building applied photovoltaics are the traditional roof-based PV that you would see on the roof. There's a few other kinds which I'll show you shortly. Building integrated photovoltaics takes the form of the actual fabric and envelope of the building itself. So it includes the roof, the facades of the building, could even include the landscaping of the building. So there's about 4 companies now in the world that have developed solar paving, which you put around the place to generate power. So really using the surfaces of the building itself to supply power to the building. The building integrated photovoltaics provide the, as I say, the envelope of the building, so the mechanical rigidity or structural integrity of the building, the primary weather impact protection, so against rain, snow, wind, hail, etc. They provide the shading, daylighting, thermal insulation to the building, fire protection, acoustic protection, the separation between the indoors and outdoor environments, and really the security, shelter or safety that is offered by the building. Other forms of BAPV, so the kind of afterthought style of photovoltaics, like you would have on the roof. There's other forms in the form of this thin film flexible PV from Heliotech. This is from a company in Germany. This is actually applied here to a mill in Dresden. The surface of the mill, blank concrete wall, by the application of the PV in this way, they've been able to achieve 2 functions for that wall. It's now providing power to operate and run the mill. Other BAPV solutions, so again, an afterthought after the fact, it's applied later on. These sorts of blind products. This is from, I think it's in these companies in Croatia called Solar Gaps. The blinds track the movement of the sun. So when the sun's at a low angle, the blades are Venetian blades are letting light through. When it's at a high angle, it's preventing a lot of light coming into the building and generating more power. So tracking the sun. Building integrated photovoltaics. They have been around for a while. They're not new as such. It's just taken a long time to kind of now kind of reach the mainstream. These sorts of products that are shown in these photographs here have been around for a long time. So this sort of monocrystalline laminated cell has been around for a very long time, and it's traditionally used in places where you don't need vision glass. So it's typically used on roofs for carports or shopping centres, walkways, places where you don't actually need to be able to see through the glass, but where you want light to come in. Other forms include the sort of type that's on the bottom photograph there. So that is the spandrel gap of the building. So between the floors, that's full PV panels that are laminated into glass and then integrated into the spandrel gap of the facade. These sorts of projects have been done globally, and this is a project in New York that was actually completed by our solar engineer based in California. This system covers the entire Whitehall Ferry Terminal in New York. It was completed in around 2006. It's a 60 kilowatt system. It lets light through, but it doesn't. You can't see out through the glass, but it does let daylighting into the building, as well as providing power generation for the operation of the actual terminal. So these sorts of products have been around for a long time, as I said. They're readily available. You can buy them on Alibaba. The two on the left are from Alibaba, on the top left-hand corner. More recent advances in this sort of space include this sort of product here from a company called Swissinso. They developed this product called Chromatics. The panels you see there are actually solar panels. Behind the metallic looking coloured glass panel is a solar panel. As you can see here from the sort of top left-hand slide how that works. The coloured layer reflects light in the colour in the visible wavelength, and the balance of the wavelengths pass through to hit the solar panel at the back. This company has about 15 colours now in its catalogue. Typically, they're all sort of metallic looking, but they do look very nice. It's a very nice finished product, and it lends itself well to integration with a product like ours, where it's the window. So then the entire surface of the building can actually serve two purposes. So we generate power from the windows and also the walls potentially in this sort of application. Another company called Solaxis have developed a similar kind of panel, but it's available in white. So if you're looking for a white product, there is one out there. Other approaches in the building integrated photovoltaic space include solar tiles. So I mentioned at the start that there's also solar paving, but solar tiles. These typically work in the same way as the product you see I showed you from Chromatics. So the tiles here are actually formed glass. Behind the glass is a very small solar panel. They work in the same way. It's very expensive. Other products in this space are like the type on the right-hand side, which is more like a traditional type of sort of Monia type tile you would see in Australia here, but they've got solar strips in the runaway sections. That brings me to window integrated photovoltaics, which I'd like to briefly introduce you to. So there's a number of products in development in this space. So all of these 4 products here are not yet available for sale, but they're in development. Potentially they're competitors to us. The 3 on the bottom from Solar Window, Ubiquitous, and Next Energy, they're actually effectively solar panels. The material that's on the glass generates the power, the product from Ubiquiti there works in a very similar way to us, using quantum dots to drive light to the edges of the glass. As I said, none of these are available, and they typically have some optical artifact left in the glass, so nanowires, microwires that if you look closely enough you can see. And at the moment they're in relatively small sizes. Products that are available on the market include this product from Polysolar and Onyx Solar, Polysolar from the UK and Onyx in Spain. Both those products typically using the glass is a whole solar panel effectively, where the material is, a lot of the solar material is actually laser ablated or chemically ablated to leave you with a panel of glass which is tinted in some way. The other approach is from a company called Pfizer in the Netherlands. They've developed a window frame effectively, which has got 3 strips of solar material around the edge. The Onyx product, at the far end of its transparency range, they have a no transparency, which is generally 57 watts per square meter. The high transparency product in their range is the second from left, generating 28 watts per square meter of power at 30% visible light transmission. And that brings me to the Clearview solution. So our approach on this has been to not interfere with the way the visible light passes through the glass. We allow the maximum visible light transmission through the glass. We look at taking out the infrared and UV and using that to generate power. At this point, I'm going to hand over to Mikhail, who's our chief scientist.
Everyone, or good part of the day. Good day, everyone. I'm Mikhail Vasilyev. I'm a lead scientist with Clearview Technologies. Please, Jamie, I would like a next slide, please, number 33.
Sure.
Okay, I would like to outline the main technology features, its advantages, and the way in which it is different from conventional BIPV and conventional PV. As would be obvious from looking at the previous slides, quite differently structured as opposed to the conventional BAPV or BIPV. And the best terminology would be WIPV, or window integrated photovoltaics, due to the fact that the energy harvesting system in our case is structured in all 3 dimensions, as opposed to single plane energy harvesting surface used in most photovoltaic systems we know of otherwise. So the picture on the right represents the core outlook on the technology features and illustrates physical mechanisms. In general, this could be called a cousin of a well-known family of systems known as luminescent solar concentrators. We place a luminescent solar concentrator right in the middle of the glazing system, which could be typically triple glazed or double glazed, additionally employing a customized photovoltaic set of modules and heat mirror type low emissivity coating or coatings, as well as specialty types of glass in most cases. Now, the main principle that can trap light within the flat slab of glass is based on a physical effect called total internal reflection. The total internal reflection is provided by the feature of luminescence. When the photons are absorbed at shorter wavelengths and are then re-emitted at longer wavelengths, they are emitted in all directions possible. Due to the optical details of total internal reflections, which many of you will know, a large number of those directions are then trapped because glass is optically denser than surrounding air. That's the only way the photons can bounce is towards the edges. Additionally, this mechanism, working in conjunction with other mechanisms such as diffraction and also scattering, reflects the incoming photons, and then a lot of them are getting bounced back off the coating and of the glass-to-air interfaces towards the solar cells placed in the perimeter region and at the edges of glass. The advantages of this approach, highly structured and reliant on advanced luminescent materials, are due to the fact that the system is conducive to receiving light from all possible directions, which means it works on the wall almost as well as it works on the optimally tilted roof. There are some academic references you can look at if you like more details, but in a nutshell, we are optimizing the most important photovoltaic quality indicator or parameter called PV yield, or energy harvesting or production yield. For example, if we place 1 kilowatt peak of installed capacity, then we on a wall on the roof, and then we measure over 1 month or 1 year how much energy in kilowatt hours was actually harvested by placing 1 kilowatt peak there. And this parameter, in our case, is optimized. And as an example, at Murdoch University in Perth, on the northern wall, the same 1 kilowatt peak of sample bundle of bunch of windows connected together generates in summer months around 47 to 53%, basically half, 50% more energy per month in measured energy output compared to what 1 kilowatt peak of silicon panels would have done on the same wall, as evidenced by online calculators and direct measurements and climate parameters accounted for. So that's 3D structuring of the energy harvesting system in the window leads to improved photovoltaic energy yield. Jamie, I'd like the next slide, please. Yes, that's one illustration. Hopefully the glowing edges are visible in the screen. A part of the luminescent emissions that our materials generate, as opposed to near infrared, are located in the green part of spectrum. And we see the edges glowing in the green due to geometrically concentrated green photons right at the edges. And strangely enough, or not interestingly, you can tell the glass system is transparent if you look across, but the edges are glowing because the photons been routed there, and part of what luminescent materials have emitted is very sensitive to the eye, and that's why we see the color. Most of the emissions are at near infrared that is fully invisible, yet the energy is transferred towards the edges of the panel. And the excitation source is natural sunlight. Images were captured in Sydney on the installation at the barbecue area roof in one of the parks owned by, operated by Sydney Council. And other photos are from the factory, from the manufacturer, obtained during routine tests of performance. I think that provides an outlook on the main core mechanisms that we use in our system. Again, the major result of structuring the window integrated solar window system in this particular way is that we are demonstrating improved energy yields. That makes us hopefully more competitive on facades, not only on north or south facades, depends on the hemisphere, but also on roofs and in installations where light needs to be collected from a range of incidence angles. I will pass on the presentation at this point to our senior engineer, Tao Zhang. Thank you.
Yeah, thanks, Misha. Yeah. Hello, everyone. My name is Tao. I'm the senior engineer in Clearview. So I'm just managing, the product fabrication and also, the product certification. So the slide you can see is that, the section for our Clearview IGU. So currently, we just offering, a triple glazed unit, and that has been certified. I can just print further in the next few slides. And you can see the system. So we got, from the top to the bottom. So the front pane is also our auto pane, so which can, withstand, the shock loading like storm and there's a weathering. So I think that answers some of the questions from you guys. So our interlayer glass in the middle. So that's a laminated glass with our nanoparticle technologies. And the bottom one, it's a low-E coated glass. So we can use a normal low-E coated, or we can use a double strip low-E coated. So it's just depending on, you know, the project and the requirements, you know, for the even like the VLT, or like a U value, or even like, you know, SHC. So both, you know, all the parameters are for the, you know, the thermal, you know, performance. Yeah, so the three black ones, you know, is our technology as well. Is for our PV strips, and basically, you know, it's like it's a fully IGU insulated glazing unit. Yeah. So Jamie, can you just please move to the next slide? So maybe our colleague, Doug, you know, he can just give some of the ideas for the thermal performance. Yeah. Hi, Doug.
Yep, currently just turning on the camera 1 second. Hi everybody. My role in Clearview is in business development, but I'm going to take you through a couple of slides that I think will answer some of the questions I'm seeing in the chat about product life and stuff. So the really unique feature of the Clearview product is the interlayer, or the PVB, or the laminate, all meaning the same sort of thing. And the key feature of that is its ability to generate power when it's not at the ideal angle of incidence to the sunlight. So most BOPV solutions, like if you were to take a solar panel up on the side of a building in a vertical position, you're going to lose a lot of production. So one of the unique features of the film and the refraction properties of the film is that we lose much less as a percentage of the peak, even when they're mounted vertically, as you would of course mount a window. So this is a unique feature of the Clearview product. So this slide is looking at what tests we've done in relation to the longevity of the PVB and the specific nanoparticles and powders we use. So this is an accelerated aging test. It was a 5,000 hour accelerated aging test, and this is showing no change in the property of the PVB in a period equivalent to 10 years on a normal building. So we expect that the PVB will be at least as long lived as any existing laminate and any existing window system. Could you do the next slide, please, Jamie? So one of the big issues, there's two types of ways, I guess, to get to the net zero. One is on the production side and the other is on the demand side. So I think, as we were alluding to before, the reason that Clearview windows are clear is because we refract the non-visible wavelengths of light to the edges to produce the power. So in our case, we're refracting about 30% of the infrared light and 99% of the ultraviolet light. And that has a benefit in terms of the thermal performance of the glass. So I guess everyone's heard of the building's thermal envelope. That is the insulation factor of a building. And the tighter the thermal envelope, or the better the insulation factor, the less energy we need to deploy in a building to maintain the particular environment we're looking for. So of course, you know, if it's 30 degrees outside and we want to maintain 24 in a building, we have to apply energy in the form of air conditioning to reduce the temperature inside the building. Same way if you're in a cold country, if it's 10 degrees outside, we need to provide energy to heat the building to make it comfortable. And in fact, the operational carbon produced by buildings that we're all talking about is driven by that HVAC energy largely. So anytime we can increase the insulation factor in the thermal envelope, it means we have to apply far less energy. And this is a key factor in reaching the net zero target for buildings. So what this slide is illustrating, this is no HVAC, this is no, it's a greenhouse, so we have a very high fenestration rate. We haven't used thermal break framing, there's no gas injection, and what we're trying to show is, although this is not the most insulated version of the product, the laminate in the glass is making a big difference in terms of the room temperature when compared to a control with single glaze 4mm glass. So we can achieve much better numbers than this actually by using our commercial, low E coatings and argon filling and stuff like that. But none of that is involved in this slide. And as you can see, there's a fairly a big gap as the day's heating up in the morning, that the Clearview window is going to save you a lot of energy. So can we go to the next slide, please, Jamie? So another question that I saw in the chat was about the product life. So firstly, Clearview is not, other than the laminate, Clearview uses existing technologies that have been deployed for a very long time. And of course, everyone's familiar, I guess, with rooftop solar panels and typical silicon wafer construction of those panels. Clearview uses silicon wafers in the collection process on the edge of the windows. Now, a typical solar panel, and also our strips that we use in our windows, degrades 4% the first year you put it up from its peak production number, and then about 0.4% per year thereafter. So our windows will maintain 85% of their peak output after 30 years, and almost 80% of their output over 50 years. So the balance of the window, or the balance of the IGU, is no different to any other commercially available glass. So if you think about the oldest skyscraper in the area where you live that hasn't been retrofitted, our glass will have a similar product life to that. The only change will be the degradation that's caused by the silicon turning the photon into an electron. Can we do the next slide? I'm seeing a question there. What's the approximate weight of the panel? So basically, I think we'll let Tao answer that. But in terms of a normal commercial IGU with a similar insulation property, the weight is very similar when you're talking about curtain wall applications.
Yes.
So the electrical components insulation, as I said, the generating component is a standard silicon wafer, the same wafer technology that's been around for ages on rooftop solar. Now, our strips, of course, are in a sealed and dry environment inside the glass unit, so they never get dirty, they never need cleaning, you're not losing efficiency from dust contamination or stuff like that. The solar strips and connection that are inside the IGU are also moisture protected because the IGUs contain desiccant, so that you're not getting condensation and in fact, all glass IGUs contain that desiccant for the same reason. Ours are not unique in that way, but it does mean that the electrical connections are in a very good place because there's no moisture. Each Clearview IGU is a self-contained system. So in other words, if we were comparing, fitting a normal curtain wall system or a normal glass window to a building, the Clearview IGU is the same fitting methodology. There's really no difference. About the only sometimes to run wiring, we may need to drill sort of a 5mm hole at some point in the structure to exit through the frame, but typically that's about the only change. The other thing that is a good thing about the product is if you walk past a building that had Clearview glass, or looked at the framing system at a building that had Clearview glass, you wouldn't be able to tell that it was solar glass from the framing system. There's no wires hanging out. It looks exactly the same as the standard window that you'd see in an everyday building. And typically we deploy, so we still have the windows are very good at dealing with the angle of incidence of the sun, as I was saying before. But of course, we still have to account for the fact that the sun is going across the sky. And depending on the compass azimuth of the building, different sides of the building will create different volumes of alternative energy, similar to a standard silicon rooftop PV window, a PV panel, sorry. So we generally deploy the product in string formations that are based on the compass azimuth, and we typically deploy the product with microinverters. So we may string 4 to 8 windows together, and then feed that power back through a microinverter, which then goes feeds the AC current back into the building's electrical system. But the installation is pretty simple, and I think we've got a slide on that coming up next, please, Jamie. So this is a single line diagram or electrical diagram of a very simple installation that we're doing on a test bed with the BCA in Singapore. But it'll give you an idea of how we wire the glass. So typically, if we were doing a big building, of course, there'd be a lot more strings. This is only an 8-window deployment, but it will give you a pretty good idea about how simple it is, really. The microinverters will give us reporting on the power generation of each individual pane of window, and also report to us both the DC current and the AC current. So if you do a building with ClearView technology, you'll be able to see the generation in real time. So typically, those microinverters, if we're doing a curtain wall installation, the microinverters will sit in the ceiling cavity on every second floor, sort of thing. So you won't see those either. So it's pretty much an invisible system, really. The only visible thing that you can see with a ClearView window is the solar collectors around the edges. Next slide. So Jamie, I guess I'll hand you back to you. I really just want to say a ClearView window can be used anywhere you can use a typical existing glass window. The installation process is really simple, and the product has a similar product life to a standard window. Jamie, over to you.
Thanks, Doug. So thank you, Tao and Misha as well. So the advantage of the ClearView product is that it's clear and functional. So unlike many other solar window solutions and sort of products that are kind of in the market, it's completely clear, up to 70% visible light transmission, unlike some of the other products that are around about 30% sort of at their best. We're generating in the sort of 3 to 4% conversion efficiency range. We can make the product very large. I'll show you a couple of pictures in the office of some sample sizes we've done for here. In terms of fabrication and manufacturing, because of the way we've designed the product, it's very easy to manufacture with fabricators in most countries throughout the world. The idea is we don't want to ship glass around the world. It's very high carbon cost to do that. It's all about trying to get the product to lowest carbon sort of cost as possible. So making as close to where you actually are going to be installing it is the sort of the real aim here. We've had the product certified in UL in the US, and for Europe, Middle East and Africa through IEC, and in Australia through the Australian AGWA, the Glass Association, and through Intertek. The product is relatively competitively priced with relatively short payback periods. It's ready to deploy. We can sell it to you now if it's of interest. So you can see here, this is Victor, our CEO and chairman, standing next to a large panel. This is around about 2.1 meters, I think. But we can go to floor plate height size now, so around about 3 meters by about 1.5, 1.6 meters wide. I've got Tao to speak to this, but I don't think we need to. You can see here that we've got extensive certifications across the board, and we're continuing to look at new areas for certification and qualification of the product, including for hurricane areas and a range of other sort of factors that might play on play on windows that are typically considered. So often we're talking to architects, and the architects are asking, is it fire rated? Well, yes, it is, but we're going further on that as well. I mentioned at the start the sort of first installation we did, which was the trial with the Vicinity shopping centre. That trial had 18 active panels. There are a number of other panels that don't get exposed to the light, and so we didn't use live ClearView panels there. The trial, in terms of its performance, proved much better than we expected. The outcome was very good. We actually, Misha Mikhail, who was speaking earlier, and Edith Cowan University, who did the research on this, published a number of papers. I think there was 2 papers at the time, and they got into the sort of top 10% of academic readership worldwide, which is quite astounding, but also I think indicative of the area of interest that is emerging around this need to move to construction decarbonisation. When we're working with customers, be they architects, engineers, developers, we're able to model their building. So if you can actually send us a DWG file or a GBXML file, we can do a quick assessment of what you're going to get back in terms of paybacks, but also power performance, and a whole range of other factors, including sort of carbon cost and things like that. Beyond that, we also work with an independent company called Solar Skyrise in Canada. They were able to independently monitor, do an analysis for us at a relatively high level, but independent. They also have the metrics for the competitor products. They can also then go to a very high level, a very detailed report, I should say, with you directly. So just on carbon payback, glass in and of itself doesn't have a real carbon payback. The literature that we've sort of come across sort of suggests that a double glazed window has around about 100-year payback time. For our product, it's around about 8 years currently. We're generating power, so it's an offset against the cost of manufacturing the glass. We know with some tweaks in our design, we can get it around 4 years, and then with some changes to the actual silicon we're using, we can get it even lower. So we, at the moment, it's around about 8 years, but we can get to 4 quite quickly. All right, so we've talked about having building integrated photovoltaics. We've talked about window integrated photovoltaics and how you can use the surfaces of your building to generate power. So that's all well and good, but then what do you actually do with this power? We worked with a company called Arup. It's a global engineering company. They had a problem. They were designing one of the most efficient buildings in Sydney. The building had Venetian blinds that were automated and connected to the building management system. To do that, they had to get power throughout the building to all floors, a very expensive and difficult exercise. So we worked with them to actually use the windows that we developed, the power that's generated by the windows, and then integrate it with a control system that can control blinds, automated switching, so switchable glass, and ventilation. I'll just run a short video that explains that a little bit better, and then I think we're just about at question time.
Imagine a smart facade constructed in glass that automatically tints glazing or adjusts automated blinds with the sun's rotation and learns how your employees like to work in response to outside conditions. An intelligent panel embedded with sensors could control ventilation, light levels, and ensure an optimum working environment that minimises eye strain, drowsiness, and headaches. To complement our energy generating glass, ClearView PV is currently developing a smart facade controller, which incorporates learning, remote management, and automated functionality based on inputs from a range of sensors. Clearview PV integrated glass panels feature a unique PVB layer, spectrally selective coating and glazing structure design. UV and IR is filtered from incident light, and part of the energy is deflected through our patented technology features within the panel towards the solar PV cells around the edges of the glass. The power generated would charge a lithium-ion battery that in turn powers a host of smart devices. Our controller can be integrated with smart building management systems, as well as residential home automation systems, such as Amazon Alexa and Google Home. Clearview PV are also looking at incorporating electrochromic and PDLC technology to enable our glass to automatically tint and adjust building temperature and lighting comfort. A prototype LED lighting facade has just been completed, seen here with both front lighting and edge lighting, both controllable from our web dashboard. The electronics and battery are integrated into the frame. Glass panels can be retrofit and are self-powering in conjunction with a suitable battery and controller. Incorporating light sensors and learning algorithms will give these windows intelligence to give a building a new lease on occupant health and well-being. By integrating a fan, natural ventilation can also be achieved with an automatic night flush, all designed with maintenance access and readily available componentry. An intelligent panel embedded with CO2 sensors could control ventilation, air movement control, and rain sensors will alert the system to close the windows or vents, all connected to the smart facade controller. A smart facade constructed with a double or triple glazed air gap could house a blind powered by a small motor, which activates in response to light level requirements of the building occupants. If the outside face were replaced with Clearview PV glass, the facade becomes a self-powering system that runs the blind motor, controller and sensors. This removes the need for cable power. Immediately there is a potential cost saving by removing a site to trade. With the incorporation of smart facades into any building design, interconnect requirements are significantly reduced, lighting running costs are reduced, and energy cost in the form of heating and cooling is reduced, derived from the efficiencies in double or triple glazing and the power generating capability of Clearview PV panels.
Just briefly, we've run out of time now, so I just wanted to quickly show you this. We can make this available as well. We've recently designed a building, an archetype which sort of demonstrates how you can get to net zero quite quickly using our glass in combination with a few other kind of building elements. The other thing we've done is we're working in the greenhouse space as well, and we've built this research lab effectively. It's a greenhouse at Murdoch University in Western Australia. On the left-hand side, that's a control room with clear glass, and the three right-hand rooms are using our glass. The idea behind this is we're seeking to prove that we can have a very highly energy efficient greenhouse, which generates most of its power needs, but also provides for a very high yield growing environment. We're currently in trials with that, and it's going very well. So I'll conclude there and allow you to ask us any questions.
Thanks so much, Jamie. That was a brilliant presentation and very informative. I can see that there are quite a few questions that are coming through, and I know that Michaela has been answering some of them. Tao, I don't know if you wanted to answer. There was one, I think, directed at you.
Carolyn, maybe you just want to run through the questions.
Yeah, yep. So I can see there's one. I'm just going to quickly go up. Kevin Flack asked a question. Currently, some building constructions prevent the rooftop use of PV due to the additional weight. Looking at the window types of PV with multi-glass layers, how can this be integrated into existing buildings if this weight cannot be accommodated?
Okay, so I think the question is that our product is not simply a BIPV product, actually it's also structure, vision, and architecture glass. So basically, it can be applied to the, the normal awning or skylights, so you could just simply, it's basically equal to the, the structure self-weight load, for the other, glass. Yeah.
Fantastic, thank you. I can see, Mikhail, you've answered a couple of those questions. Jachin has asked, are these available for purchase? Do you have an approximate retail price?
So I might speak to that one. I did actually put an answer on the chat. Yes, they're available for purchase. The price depends very much on the specification. Are we doing what coatings we're doing? What are we doing, an argon fill or whatever? But typically, the product is very similarly priced to a high insulating IGU. Curtain wall stuff, for example, it's not much more expensive, and the payback period comparatively is reasonably short. So particularly for curtain wall applications, the glass is extremely competitive.
Brilliant, thanks, Doug. I think you guys are answering them all in the chat box. So I'm just looking down and I can see that you guys have actually responded. Joseph asked, can this technology support tie grid mechanism as traditional solar panels?
Yes, we're doing this already at Murdoch University Greenhouse, and we are exporting to grid as well as importing from grid. So it's, given enough windows, more than a couple dozen windows, it's worth exporting for sure. And typical installations will involve hundreds or thousands of windows, which means every floor of an office building can have its own separate meter exporting to grid.
All right, fantastic.
Yeah, so every project is different. We would look at the project with the client. So it can either be going to a battery on the floor to power, lighting and functionality for that floor.
Yeah.
You can go to a basement or a roof where there's a large battery for the whole building, or it could be that there's you're looking at the sort of smart facade sort of solution that we have there, where each window can provide power to something at the window itself.
Yep. Okay. Brilliant. And Leslie's just asked, is in areas where there is a rough climate, can this type of PV accommodate those areas?
Yes, absolutely. So yeah, Doug, you go ahead.
Well, I guess I can talk to that. Was that a rough climate, did you say? Or?
Yeah, that was my question. What is a rough climate?
A rough climate. So I'm not sure.
Okay. So basically, the glass will work in any climate. Yeah, the colder climate or hot climates, it's very similar properties. We're actually doing some testing in Singapore at the moment to see how the glass will handle. It's not so much the heat of the island or whatever like that. It's the way the sun tracks across the sky and how that affects the generation. So we're actually doing some testing in an equatorial country to see how that will work. So we know the numbers in the Northern Hemisphere, and we know the numbers in the Southern Hemisphere. We just haven't done the middle yet. But typically, the glass will be effective both climatically and energy generation wise, whether it's hot or cold. If you're talking about storm certification, wind speed certification in hurricane areas and typhoon areas, yeah, the glass is certified for that. And in fact, the glass also has some good benefits security-wise because of the thickness of the glass and the way it's constructed. So it's very strong IGU, and probably as strong as you would get in any normal sort of skyscraper glass or security glass.
Wow, that's incredible. Thanks for that. I can see quite a few questions coming in, and I know that we're past the time. I'll just finish off with one last question. I can see Meshach has asked, what's the lifetime? But I believe that was answered within the webinar. Someone has asked how much percentage of IR and UV are deflected and convert to solar cells in the frame?
So the answer to that is 99% of the UV rays and roughly 1/3 of the IR spectrum.
Thank you. Well, I think we're going to wrap it up now, but thank you so much for joining us today to present. It was a very, very fascinating presentation, and it's great to hear these new technologies, especially with what's going on in the world with climate change. So thank you. And for everyone, online today, we will be sending out the presentation slides, and Clearview, if you guys have got anything else you'd like to add in for us to send out, please feel free to send that through, and we can send it out to attendees. And I think that's about it. So
Caroline, our contact
Yes.
details are on the slide. If they've got any questions, we're happy to speak to anyone really.
Brilliant.
Yep.
Thanks, Jamie.
All
And
right.
yeah, it's been a great session tonight. So I hope everyone has a wonderful day or evening wherever you are in the world, and we look forward to seeing you online in our future Tech Topic webinars. Have a wonderful evening. Thanks.
Thank you.
Yeah.
Cheers.
Thanks, Gary. Yeah. Thank you.